My name is Goran, and I'm the presenter of this presentation, and the author is the Xia Lifang, and he cannot hear, so I will speak behalf on him. I will continue the semi-Holland's topic and focus on the art, on the RISC-V processors, and on our XuanTie C920 processors. So what's the art? Art means Android runtime. It firstly introduced by the Lollipop, and when you write your Android application with Java and Kotlin, and it first would compile into the language machine bytecode. And in the Android, it's called art bytecode or the DEX bytecode. And it stored the DEX file. And art would pre-compile the DEX field into the machine code and stored it in the OAT file. And during the installation, and the art would execute the machine code directly when the application running. So this mechanism we call ahead of time compilation, short in the AOT. And before the Lollipop, there are another mechanism which is called DAVIC. DAVIC is a virtual machine could directly interpret the bytecode and improved with the just-in-time compilation, short in JIT. That means he would concurrently compile the bytecode into the machine code. And the next, the DAVIC would directly execute the machine code just like the art behave. So the disadvantage of art is it would pre-compile all the stuff into the machine code. That would cost most of the storage and the memory footprint. And the DAVIC, but the advantage of the art is it could execute very fast. And the DAVIC is you could directly execute the bytecode. It could save a lot of memory footprint. It could in the Android early days, it could it's suitable for that tight memory devices. But the disadvantage of the DAVIC is it would cause some performance gap because you need concurrently compile the bytecode into the machine code. So today's art combine the DAVIC and the AOT together with the hybrid compilation. So there is interpreter, JIT, AOT together. So here is the full diagram of today's art. And when the Linux bring up, and just like the traditional Linux init, and it would call the Android first init process application is called a Zygote. And the Zygote would depends on a lot of libraries to support the Zygote running. So Zygote is the entry of the Android world. So it's the first process that of Android, and the Zygote would start the art environment and start the first Java Kotlin application. Yeah, and all the service process, interactive process, or the application process are forked from the Zygote. So that's how the art started from Zygote. When the art started, it could use the interpreter to directly execute the DEX file and speed up with the JIT method. And then it also could run with the AOT style, but this AOT is improved with the profile-based. So it's called profile-based AOT. That means when we install, during the installation of the APK, and we would according to the profile field to compile the DEX file to the OAT files, and we just compare some startup method and halt method. So that would reduce the installation time. And during the running, if your device is charging or in the idle state, the AOT would background work to continue to translate the bytecode into the machine code according to the profile. And the profile also generated by the art, and it also could upload to the cloud. So that's the whole art. And the art could directly call the native libraries with the native Java interface, and also it could call the DEX Java function or Kotlin function stored in DEX art libraries. That's how art works. So what we focus on is, for the RISC-V porting, we focus on the interpreter and the JIT and the compiler. Both the JIT and the AOT based on the compiler. So that's named is the DEX compiler. So here is the DEX compiler hierarchy. Just like the normal compiler, they have the front end, they have the intermediate representation, they have the optimized code generation, and the microassembler. And what we focus on the RISC-V porting is the backend component, such as the optimized last stage, instruction similar intrinsics, and code gen with the coding convention, location, instruction, code gen. And we also need to put all the instruction set in the macro assembler, such as the standard RISC-V instruction set or our customer instruction set. So let's go back to the story days of the RISC-V art initial story. So we started the Android porting 3 years ago, yeah, and it's based on the Android 10. And I remember it's on the March 2020, we began our project, several folks involved. And we started with our test chip, only 2 cores in the test chip. And we started with the Linux kernel drivers, and we porting the CLAM and build system, soon build system, and we also porting the Bionic. And then we hit a shell without a Zygo to the compiler guys. And then the art porting we started in the general 2020. And we begin our first list, we began our the simple interpreter and just implemented Gen I coding convention. When this is ready, so the whole Android could work, the Zygo could running, and that takes about 20 minutes to launch. This is happening in the August 2020. And when the basic interpreter ready, we began to find a way to improve our speed. And we found that, oh, it's a faster interpreter named mterp. So we put in the mterp, and when we finished work, it's reduced to the 10 minutes. Yeah, and that's finished in August. And in the April 2021, we finished the compiler. That's a hard start. That's a tough work, yeah. And when the compiler ready, the JIT AOT all could work. And that's reduced the boot time into the 1 minute to the launcher. So the right picture show is our is that time we have, when we started up Android, we announced to the world, and it's spray out the world. The news is very famous that time. It's a good memory. That's happening in the April 2021. And next, we started with Android 12, and based on our newest chip, and named TH1520. And we started with the traditionally with the kernel, with the drivers, and we also updated the CLAM 12 to the 15 in the Android 12, because a lot of RISC-V features, our customer instruction features are in the CLAM 15. And we also updated Bionic. And then we again started art porting work. This time we changed the mterp to the nterp, because nterp have a lot of improvement of the interpreter. And also it have the XT header extension. And then after tons of the tuning, our product, our right picture have showed it's called the LichPi boot time gets about 47 seconds and less junk. So you can try this board on our booth in the expo hall. Yeah, we have the demonstration on our booth. And then we started upstream story. Yeah, we started upstream. We started it at September 2022, and we firstly started with the standard RISC-V OSP configuration file. And we finished the basic interpreter in the March 2023, and we finished the nterp in the June 2023. 2023, and Lars Bergström demoed this his catfish emulator on the RISC-V Summit in Europe, and it's also a very famous news. And in the October, just 3 weeks ago, we finished the compiler, and when the compiler is ready, the AOT and the JIT all can work. That means if you download this AOSP again and try the demonstration again, you will get a better experience. And now we are continuing contributing with the intrinsics of the DEX compiler, and of course, including the vector 1. And thanks to Google guys' help, reviewing, optimizing, and merging. And here is all our contributions. And here is some open discussion on the Android ABI. Yeah, and firstly, Google has announced the Android ABI with the RVA 2022 with the vector crypto, but the problem is there is no hardware supported now. And our next generation of our processor all supported this, but the current hardware, including other vendors, cannot support it. So Semiholland sent a patch to make it work around. We also like this patch, and we also want a similar patch of this. That means, but the difference is we want to add our custom instructions to the AOSP. Yeah, it's more complex than just getting them manipulate. The reason is that it could improve the performance, and we use about 50 instructions to improve the art. And every components here we summarize our optimization method. Yeah, and after this optimization, compared to the standard basic RISC-V ISA, we got a significant improvement in the benchmark. That means the art is very sensitive to the instruction design, especially in the middle or low processor. Yeah, that means a powerful instruction could help art work efficiently a lot. In the CaffeineMark, we got about 20% improvement. And in the scientific math library, too, we got more than 30% improvement. And in some other benchmarks, some small benchmarks, we find 5 times improvement. That's exaggerated improvement. That means bit manipulation extension is very necessary because basic ISA is really not enough. So that's why Android ABI involved the RVA 22. Yeah, here is the diagram we have tested. You also could compare the bit manipulation like this, and we would open the method. Another top, okay, oops, okay. So in this discussion point is we want how to let the existing hardware could run AOSP properly during the upstream. Another topic also is about ABI. We saw that the Android have a big opportunities in the wearable devices, tight memory devices. So how about, let's think about 64 ILP32. And this has success in the Apple Watch. So so I want to get some feedback from the Android expert to how about ILP32 ABI get into the Android. The advantage is this ABI no change to current hardware ISA definition. So this just software data type change. And another is could reuse most of the current outputting code. And it will bring extreme benchmarking, such as the spec-int CPU. And we have finished the Linux kernel and the GCC work and the spec-int CPU benchmark. We will talk more in the Linux Plum conference conference, RISC-V micro conference. Yeah. And it also could save memory footprint, and it could compete with old LP32 code. And the disadvantage is another ABI would cost the maintenance work, would cost a lot of ecosystem API porting work. So that's all. So summary in 2 discussion points. One is how to let the existing hardware run with the LSP, and the second is how do we think about LP32 API in the Android? Yeah. Thank you very much.
Thank you. So, any question? We have time for 1 or 2 questions. Anyone? Questions? No, I think that's it. Thank you very much.
Okay.